Okay, n is greater than this. So n is greater than 7 means our m is 7 here, and n is also natural number, so n will be 8, 9, 10. These values are of n. So what is the meaning of this limit? If we take here, what we get? 5 upon n plus 3. This we get. Okay. So if we write n value is 8, 9 or 10 or more than this, then this quantity always less than 1 by 2. Okay. So what the meaning? Meaning is this is 1, 2, 3. Suppose here 8 will come. Okay. 8, 9, 10. Okay. And here we write 3 by 2, and this is 2, and this is 5 by 2. Where these come? For you know, an minus l less than epsilon. So from this what we can write? Minus epsilon an minus l. This quantity you can write. So l you can add. So l minus epsilon an l plus epsilon. So l we know this l value is 2 here, and epsilon is 1 by 2. So what is this? This is 3 by 2 an, and this is 5 by 2. Since here if we take the value of n 8 or greater than 8, then always the value of this sequence lies between this. Means if the value is greater than 8, okay, greater than 8, then always the value of the sequence lies between this interval b by 2 to 5 by 2, you can see. Okay, so here our task is to find out m. Okay, when n tending to infinity means n is very very greater value, then the limit will be 2. Okay, more value means this interval will be less. Okay, so this is the meaning of this definition.
Sir,
Yes,
sir, in definition there is n greater than equal to m, but here is n greater than m only.
here in the definition n is greater than m. Okay, so
Okay.
here m is 7. You are getting, and n is greater than. Here m is fixed value. Okay. Here m value is fixed. Okay. So n is variable. So n is greater than m. M is 7. So n value will be, because n is a natural number. So n will not be 7.5 or 7.3. N will be 8, 9, 10, these values. Because the sequence definition, you know, from natural number to real number, the definition. So in the domain, n will be a natural number only. Important results are there. Results we have to remember. First one is every convergent sequence is bounded. Convergent sequence, you know, if the limit exists and unique is finite and unique, if you are getting that sequence is a convergent sequence. But converse may or may not be. Okay. So in the previous here, you know, that here limit exists. So this sequence is a convergence sequence because we have the bound of an. An sequence is there, so an value is always greater than 3 by 2 less than 5 by 2. So this is bounded. So for every convergence sequence we can find out the bounded above element and bounded below element. So every convergence sequence is bounded, but the converse part you cannot say, means every bounded sequence is convergent. We cannot say. Why? By taking the example, if I am taking, this is a sequence minus 1 to the power n. This is bounded sequence. Here bounded below element is minus 1 and bounded above also, because in the range set if you see minus 1 and 1 it will come. So this is bounded sequence, but this is not convergent because when we find out the limit, here the limit is not finite but not unique. Okay, so this is not convergent. So here converse part is not true. So depending on n even or n odd. So this is not convergent. Okay, so every convergence sequence is bounded, but converse may or may not be true. So this is the first result which we have to remember. Second one is,
Can you please show the previous thing?
yes,
Yes, sir.
now every monotonically increasing sequence increasing sequence which is bounded above converges. Okay, so this is one of the criteria to show that the given sequence is convergent. Means if, because for all the sequences you cannot find out the direct limit. Direct find out. So by using this criteria, you can find out the limit. Okay, what is the criteria? If criteria is if monotonically increasing sequence and plus bounded above, means increasing sequence if you are able to see, increasing you know how to show, and bounded above. These two value if you are showing, it means the sequence is convergent. Okay. Third one is if decreasing plus bounded below. Decreasing plus bounded below if you are showing, it means also convergent. So these two criteria are also there. So that given sequence is convergent. Every increasing sequence which is not bounded above, which is not bounded above, diverges to infinity. Okay. If increasing sequence is there but not bounded above, then that sequence will always diverge to infinity. Every sequence is not bounded below diverges to minus infinity. Okay. Now next one is a monotonic sequence either convergent or divergent. Convergent or divergent. Okay, means if increasing sequence is there or decreasing sequence is there, then if means you are able to find out that is increasing plus bounded above, then convergent. Decreasing plus bounded below, convergent. If increasing but not bounded above, then diverges. Decreasing but not bounded below, diverges. And if it has the monotonic property, means increasing and decreasing, then it will always either convergent or divergent. So if the given sequence is given by 1 plus 1 by 3 plus 1 by 3 square, this is a sequence. Okay, so in this case, here to find out the limit of the sequence is not easy task. So to show that this sequence is convergent, you have to show that this is increasing sequence where bounded above element exist. Then you can show this sequence is convergent. How to show this is increasing or decreasing? So first we find out xn plus 1 term of this sequence. Okay. So xn plus 1 term will be 1 plus 1 by 3 plus 1 by 3 square plus 1 upon 3 to the power n plus 1 upon 3 to the power n plus 1. This is xn plus 1th term of this sequence. So you can subtract this. So what you will get? 1 upon 3 to the power n plus 1. Okay, because n here natural number, so always this value will greater than 0. So greater than 0, what we get? Xn plus 1 minus xn greater than 0, or you can say xn plus 1 is greater than xn, means you are able to show this sequence is increasing sequence. Okay, this sequence is increasing sequence. And now here we find out what is the bounded above element. If bounded above element exists for this sequence, then this sequence is convergent sequence. If not bounded above, it means diverges to infinity because this is increasing sequence. So to find out the bounded above element, we find out the sum of this sequence. Sum to find out, because this is a geometric series, so the sum will be, first term to 1 minus r to the power n plus 1, whatever. So this 1 minus 1 by 3. This is the formula to find out the sum of the geometric series. This is a term of this sequence. So the sum of this sequence by given by sum of geometric series. Okay. So here, if you compare this 3 by 2, 1 minus 1 upon 3 to the power n plus 1. Okay, because this is increasing sequence. So if we find out, we take n tending to infinity, then here we will get 3 by 2. So here the sum of xn is this. If we take n tending to infinity, so we will get 3 by 2, means at infinity the term is coming 3 by 2, means the 3 by 2 is the bounded above element. Okay, so 3 by 2 is the bounded above element. So this is bounded above element. So here you are able to see that sequence is increasing plus bounded above element exists. So this implies the given series is the given sequence is convergent. Yes. Next, decreasing plus bounded below. We have to find out then. So xn sequence is given by n plus 1 upon n. This is xn sequence. Now we have to show this is a convergent sequence. So by that criteria means in case 100 below, you will see here means n plus 1 upon n. What is xn plus 1 term? Xn plus 1 term is n plus 2 upon n plus 1. N plus 1 minus, then you will get minus 1 upon n plus 1. Okay, this term you will get, so this term is less than 0. So because n is a natural number, so less than less than 10 means you are able to prove the given is a decreasing sequence. Given decreasing sequence between plus 1 upon n, this becomes upon n plus 1 plus 1 by n. Now for n tending to infinity, we get this. So always this sequence is greater than equal to greater than 1. So what is this? This is the bounded below element. So plus bounded below element you are able to find. So in this criteria, the sequence is convergent sequence. Okay. So in this way, you can write. Now, next one is okay. Yes. Now, question is prove that 1 upon 3 to the power n converges to 0 by definition. By definition means by the definition of limit. Okay. So here Your task is to find out the value of m. Okay, to value of m, the task is. So this is converted to 0 means limit of this sequence is 0. Okay. Now for epsilon greater than 0, what you can write? An minus L less than epsilon. Okay. For n m. So here our task is to find out m. M is fixed, n is variable. To understand this thing. So here we can write the value of this sequence 1 upon 3 to the power n. This is 0, this is epsilon. Okay. Now, from this what we have 1 by 3 to the power n is this. Okay. Or we can write 3 to the power n is greater than 1 upon epsilon. Now, because here you have to find out the value of m, so you can take log, taking logarithmic both the sides. So what you have n ln3 greater than this. Now n greater than and here ln. So here we have this is a fixed quantity epsilon is given and log 3 is fixed. So here we can find out the m. Okay, which is lies between n and m, means in this value. If you calculate value, suppose this value is coming 0.01. Okay, so you can write m is 1, so n is greater than 1. This value always lies in that interval. Okay, whatever the interval you are getting means bounded, because this is convergent, so lower bound and upper bound you have. So the meaning of this is that here we are able to find out m. So because this is a fixed quantity, so you can find out the value of m such that this. Here you can write this value is equal to m, because from this value next integer value, the value of m. Find out m, so you can write 1 by 3n
Sir,
is,
n greater than m.
yes,
Sir, n greater than m. But it is not
yes.
necessary, sir. M will be greater than this term also.
Why this is not necessary? If you are getting suppose any value, you can say give the value of this for any epsilon. The value of this is suppose 1.2. So you can find out m is 2. So n is a natural number. So n always greater than 2. M is fixed, n is variable. Means for n greater than m, this sequence will converge. Means after greater than 2, this value always lies in that interval. In the bounded above and bounded below, means in the interval means an less than l plus epsilon and l minus epsilon. In this interval always the value of the sequence will lie. If this happen, now what is your doubt? Tell
Sir,
me.
n can be equal to m, sir.
N, yeah, n may be equal to the m also.
When ln 1
This
by
is,
epsilon upon ln 3 is equal to integer now.
yeah, that value will be integer. Means not integer. That value may be any real number, but you have to find out next greatest value. Suppose 1.2 you are getting, then next integer you have to find out greater than this value.
No, sir. Let's say epsilon equal to 1, sir. Then n equal to m equal to 0, sir.
Yes, if epsilon equal to
Sir,
1
if epsilon
uh,
equal to 1, then n equal to m equal to 0, sir.
1 minute. If epsilon equal to 1, okay,
Yes, sir.
then this value is coming 0. So this value is coming 0 means
Yes,
you
sir.
can find out m is equal to 1. Okay, m is equal to 1 you can find out, and all values greater than 1. Okay, because here n is greater than m. So after 1, this value of the sequence lies in this interval. In this interval means an L plus epsilon and L minus epsilon. Epsilon you are taking 1 and L is 2. L is 0. L is 0, okay. Epsilon is 1. So minus 1, and this is an, and L is 0. Epsilon you are taking 1. So for n greater than 1 means for n equal to 2, 3, 4, 5, always the value of the sequence lies in this interval. Now tell me what the doubt.
No, sir. Understood.
Okay. Now, so in this way you can prove by definition that 1 upon 3 to the power n converges to 0. Now, here also for the sequence there is a squeeze theorem or sandwich theorem to find out the limit, or sandwich theorem also. Okay, if three sequences are there, xn sequence, yn sequence and zn sequence. Three sequences are there such that xn less than equal to zn less than equal to yn. Okay, then if limit n tending to infinity xn is equal to L, which is also equal to the limit of yn. Okay, if the limit of this and limit of this exist and equal to L, then you can say the limit n tending to infinity of Zn is also L. This is the theorem or sandwich theorem. So now we take one example how to apply this.
Previous slide, please, sir.
Yes.
Done, sir.
Find out the limit of this sequence. 1 upon n square plus 1 plus 1 upon n square plus 2 plus up to n square plus n. Okay, this is the sequence. Find out the limit of the sequence. So, we can apply here. N equal to sequence means 1 upon n square plus 1 plus 1 upon n square plus 2, 1 upon n square plus n. This is let n. This sequence is always greater than or when if we are replacing this value means all the values with this, n square plus n means in place of 1 upon n square under root n square plus 1, 1 upon n square plus n, where n is a natural number, you can see. Okay, so if we are replacing this, then always the value of the sequence will be greater than equal to this value. This is what you can write here. Here you can write n times of under root n square plus n. Suppose this is xn. Okay, suppose this is xn sequence. So here we are able to find out that the sequence value is always greater than, from this sequence we can find out the less than. An sequence is n square plus 1, n square plus 2, now 1 upon n square plus n. This value always less than equal to 1 upon n square plus 1 plus 1 upon n square plus 1, means all the values we are replacing by 1 upon n square plus 1. Okay, means we are decreasing the denominator. Okay, so this value always greater than equal to n times of n square plus 1 our yn. So here the given sequence is an, okay, and we are able to find out yn sequence and xn sequence. So by Squeeze theorem we can find out the limit of xn sequence into infinity xn, and here xn is n upon n square plus n. The limit, when you find out, the limit will come 1. Okay, and you can take common, then the limit will be 1. And similar way you can find out the limit of this yn. So limit n tending to infinity n upon under root n square plus 1. So this is also 1. So it means the limit of the given sequence is also 1. In this way you can find out, because here directly we cannot find out this limit. Okay, there are another method also to find out the limit of this sequence. Directly you cannot put the n tending to infinity. Okay, because infinity plus infinity is indeterminate form. Okay, so here you are find out the limit of the sequence by Squeeze theorem or Sandwich theorem. There are two formulas also there to find out the limit, which is theorem on limit, Cauchy first theorem on limit. Here Cauchy given two formulas. First formula is the first theorem on limit. So here what it says, if limit tending to infinity of an sequence is L. If an sequence the limit is L, then the limit n tending to infinity of a1 plus a2 plus an upon n, for this sequence also the limit will be L. This is a formula given by Cauchy first theorem on limit. The proof of this is not in your syllabus, so just you have to remember the formula. If the limit of this sequence is L, then the limit of this sequence will also L. In the previous example, if you want to apply this
Sir, your voice is breaking, sir.
Okay. Hello. Yes. So I want to say that if we apply this formula on the previous example, this is the previous example. Here you have to find out the limit. So we apply this formula. By this formula, we find out the limit of this sequence. So limit n tending to infinity. Okay, we can write, because the given sequence is under root n 1 upon this 1 upon under root n square plus 2 1 upon under root n square plus n. This is the question which is given. You have to find out the limit, and we have this formula. So what we can do, we can multiply in the denominator by n, okay, and numerator also n. We can multiply numerator and denominator by n. Okay, so what is this? If you compare this with this, then what is the value of a1? A1 value is n upon under root n square plus 1. What is a2? A2 is n upon under root n square plus 2. And similarly, what is an? An is n upon under root n square plus n. So by multiplying n upon in the numerator and denominator, we can compare with this. Okay, here we have to find out the limit of this. So by this formula, if the limit of an is L, then the limit of this sequence will also L. So here an is this. So we can find out the limit of an. Okay, limit of an is n upon under root n square plus n. The limit will come 1. So the limit of the given sequence, will also L. Here you can write then by Cauchy first theorem on limit, you can say the limit of 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 up to 1 upon under root n square plus n will also 1. So in this way you can apply the Cauchy first theorem on limit. Now, Cauchy second. Next is Cauchy second theorem on limit. What is the formula here? You can apply the formula if all positive. If all the terms of a sequence an are positive and limit n tending to infinity an plus 1 upon an is L, which is exist, then limit n tending to infinity.
Sir, previous slide, please.
Yes.
Thank you, sir. Okay, sir. Thank you,
Here,
sir.
yes. In the second Cauchy second theorem on limit, what is saying? If the sequence is of positive term and if the limit of an upon an plus 1 upon an is L, which is exist, means unique and finite, then the limit of this sequence means an to the power 1 by n will also L. Okay, for example, out the question is find out the limit n tending to factorial 3n upon factorial n to the power 3 to the power 1 by n. Okay, you have to find out the limit of this. Okay, so here let an equal to 3n factorial upon factorial n cube. So this is an. So here we can apply the Cauchy second theorem on limit. So we can find out an plus 1. So what is an plus 1? 3n plus 3 factorial upon n plus 1 factorial to the power 3. Okay, now you can find out limit n tending to infinity an plus 1 upon an. Okay, an plus 1 you have, you can calculate this limit will come 27, you can try. Okay, so the limit of this is 27, so the limit of this also 27 by Cauchy second theorem on limit. Okay, if this limit exists, then this is equal to this. Okay, so in this way, by Cauchy second theorem on limit, you can say the limit of an to the power 1 by n is also 27. What is an? An is this we let. Okay, we have to find out the limit of this to the power 1 by n. So we can find out the limit of an plus 1 upon an. So whatever the limit, that limit will be equal to that. Okay, so in this way, okay, so these are the various formulas for find out limit. So in the next class, we will see some more examples and some sequences and how to prove that the sequence is convergent. Because if the terms are not given by on single sequence, means suppose a1 is root 2, this is given, and an plus 1 is given by this, where n is greater than equal to 1. Okay, if this sequence is given by a recurrence relation, okay, by a recurrence relation, then how to prove this sequence? Because this is a sequence where first term an is a sequence where first term is given by this and remaining term given by this recurrence relation. So you have to prove sequence is convergent. So here we can apply that that note that if you are able to prove this sequence is bounded, means increasing or decreasing, plus increasing than bounded above, decreasing than bounded below, then you can say the given sequence is convergent. Directly here we cannot find out the limit because we don't know this is a convergent or divergent. So convergent or divergent, if the terms are given by a recurrence relation, you can prove by that theorem, means increasing plus bounded above or decreasing plus bounded below. Okay. So if this is convergent, then limit is unique. Limit is unique means limit of an plus 1 also L, limit of an is also L. So by putting here, you can find out the limit. So in the next class, we will see how to solve these types of questions. Okay. So this is all about today. Any doubt?
Sir, yes, sir. So one doubt.
Yeah.
Sir, in that question, under root 1 upon under root n square plus n, can you go to that slide?
1 minute. Yes.
Probably no. Yeah. Sir, here, when we were evaluating, we multiplied the numerator and denominator by n, right?
Here, okay, 1 minute, 1 minute. This is not that question. Yeah, here this is the question. Yeah, here we are multiplying the denominator and numerator by n. Yes.
Yes, sir.
Yeah.
So, according to the definition, it should be limit n equal to L, then limit n tends to infinity, sum of all divided by n, sir. So here when we
Yes.
are multiplying in the numerator, aren't we changing the series itself, sir? That should be the original series divided by n, no? Like the numerator n shouldn't be there. We are multiplying it extra, sir.
No, no, here we are multiplying not extra. Here multiplying in the denominator also, in the numerator also. So no change in the sequence. We can multiply any term, any sequence in the denominator and numerator with the same value we are multiplying, then no change. N is
Sir, then
positive.
this is
Hmm.
again a1 plus a2 plus dash 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 an only, no? There is no n divided then.
No, no, no.
This is
See, this is A1 value. This is
yes.
A2 value, this is AN value. So what we can write this? This we can write A1 plus A2 plus AN upon N. You can see, here you can put these values. Then you can compare.
Sir, then the a1 plus a2 value that we are putting here and the
Yeah.
a1 plus a2 value that was in the original series can be different.
No, no, no. Original. Why this is different? You can put.
Sir, so
See.
numerator is containing another n then.
1 minute, 1 minute, 1 minute. Here limit n tending to infinity a1 plus a2 plus up to an upon n. Okay, we are putting the value of a1, a2, an. So
Hmm.
a1 is this. Okay, and a2 is this.
Sir, but in the question it was 1 upon under root n square plus 1, no? So what I'm saying is ki here that original question thing should be put 1
1
upon
minute.
under root n square plus 1 upon under root n square plus 2 upon n, not the n in the numerator.
No, here we are multiplying in the denominator and numerator, na. So a1 is this, not here. This 1 upon under root n square plus 1 is not our a1. Okay, because we want this sequence, that's why we are making this is a1, not 1 upon under root n square plus 1 is a1. A1 is this. Here n in the numerator. Okay, then here if you can write, then here if you take n common in the numerator and denominator, then this sequence will be the original sequence. So if you compare, then this is our A1 and this is our AN. So A1, AN means we can find out the limit of this because this and this are same. So we can compare here. But here, if you want to compare, see, if this is the limit and this is the original question, if you are comparing here with this, so you cannot compare because in the denominator n is not there. So how you can compare, how you can take an is 1 upon under root n square plus n? In this form, the given question is not there. So how you can compare? Tell me.
Yes, sir. So limit extends to n, like limit extends to f of x upon limit extends to g of x. We can directly write limit extends to f of x by g of x. So we will directly multiply limit I n tends to infinity, and we can write limit n tends to infinity by like original
No, here you
expression by.
cannot write. Here the terms are means here you cannot write that limit of f of x, limit of g of x. Here because this is a combined sequence. Okay, this is not a different part. Here, this is the way only. Either you can apply the skew theorem, either you can apply the Cauchy-Firth theorem on limit, and a lot of other methods also to find out the limit. Here, the limit is 1. So, to compare with this form, we are multiplying and dividing by n. Because in the original form, you cannot compare with this form. So, you are if you are not compared, then you cannot apply the Cauchy-Firth theorem on limit. To apply the Cauchy-Firth theorem on limit, you have to multiply. Okay. So this is the case. So this is all about today. Next, if the recurrence lesson form is given, how to prove conversion, we will see in the next class. Okay, thank you.
Sir.
Yes.